2, 1, so welcome in. So let's try to define pressure in physics. Typically, you're going to get kind of acquainted with pressure whenever you're studying foundational, possibly maybe fluids, right, and then the flow of fluids. But it applies to anything. So you can certainly define pressure with regards to kind of any force that you have, which is spread over a surface. So I want to just give you kind of a glance. So here on the screen, you can see that I have taken pressure right there, and I define it with respect to the normal force that you have present over a unit surface area. So this isn't a very difficult definition to think about. So pressure here is going to be the little p that you have, and then you have your force, which is the normal force, which I'm going to explain in just a moment, and it is being divided by, so it's spread over a particular area. Now, the area can be anything. So it could be possibly a rectangle, could be a circle, could be a triangle. So those are the three that you kind of should be familiar with, right? So that you can have the skills to be able to calculate those. And now very often, so instead of writing this little normal here that we have, this n and sometimes maybe a small n, we're going to drop it. So you're going to see this written just simply as force over area. Now, what do we mean that it is the normal force and it is being spread over a surface area in general? Okay, so let's take a see, okay, and how this actually works out. So the first thing, with regards to the normal force that we have, I want you to keep in mind and hopefully understand what it means to be perpendicular to a particular surface. Okay, so I want to talk about that so that you can grasp this entire concept. So let's imagine. So I'm going to just draw a particular box. Okay, I'm going to do it in a fast forward fashion. Okay, so I'll be right back. All right, so here we go. So here's a box, okay, and let's imagine that this box itself is sitting on some kind of a table. So there's a surface that you can see there. So this is the box that I'm referring to, right? And we can place it, anywhere on the table right here. So let's imagine that it is sitting here. Now, this box is going to have some kind of a weight, right? So any box, if it's going to have some mass, it's going to have a weight. And now, if you have a weight, so as you know, the force of gravity is going to try to pull it down. And then you have a force of normal, which is kind of from Newton's third law. So for every action, you have a reaction. So this is the reactive force, where the table is kind of pushing back, right? Now, as you can see here, so on the actual table, so what you might have is, so within here, so let's say that I'm going to draw this and I'm going to just kind of concentrate here on the base itself, right? So this is the base, okay, of the box, okay, that we have. And I'm going to just shift it out, okay? You can imagine that that is the actual base. Now, that base is going to have an area, right? So as you're kind of going through here, well, it's sitting on this, and you can certainly calculate what that area is. That area would have been just nothing else but length, multiplied by the width, where, this is your length. So it's from here to here. So let's imagine that's the length. And then this is your width from here to here. So that's your length and that's your width. So this is going to have that particular area, right? So that's not very hard to understand. So I'm going to put a little A over here, and that's the area. Now, that box, because of its weight, is going to distribute its weight across that entire, base. So it's the force itself is not going to be at a point, but it's going to be spread over that particular surface. So the weight itself of that box, you can imagine that this is going to be kind of pushing it down. And I'm going to draw a lot of arrows in here. So I'm going to kind of just start duplicating these, so that it just shows us that it's being spread around all over. Now, of course, it's uniformly spread, and, hopefully that the surface, the base itself, is kind of uniform. But, you can kind of get the idea that, this force is being pushed down on this entire surface. And this is where we are kind of talking about what pressure is. So pressure is the calculation. The area itself should be easy for you to understand. Okay, so it's the area that the box is sitting on. And then the actual force would be coming from the weight. Now, the normal force is always perpendicular to the actual surface. So if I would kind of steal this, right, and I'm going to kind of take this out and I'm going to duplicate it and now put it on the other side over here, what we are referring to, perpendicular would have been, so if you took that and you made it perpendicular right there, it would have made a 90-degree angle with that surface, right? So it would have been kind of straight up. And that's what we're interested in. We're interested in the component of the force that is spread out over the surface, but it's the component that is perpendicular. And you might say, well, what else can it possibly be? Does it have to be, something different? Is it at an angle? No, it's not. It's just sitting down. And that's a good thought process from someone, okay, that is thinking about this. But that's, of course, in terms of stationary forces that are just kind of are sitting. But imagine, someone is poking at this surface, right? They don't have to poke straight down. They can poke at an angle. And when they're poking at an angle, you might say, oh, well, now, you can spread this force at an angle, right? Which is pushing, okay, at an angle like this, right? But it's still a force. So this, okay, kind of would have been the force. I'm going to put kind of A for applied force that we have. And what you would have been interested in is the component which is perpendicular. So you would have taken this force right here, and you would have been trying to find what is the actual component of that, which is going to be perpendicular to it. Now, I'm not going to go into this video in terms of trying to figure out, okay, how to get the angle and then work with trigonometry. You can certainly take a look at that somewhere else and down the line as you go further and further. But in introductory physics, we typically will make that assumption that it is perpendicular. And if it's not, your teachers will tell you, and then they'll provide you the tools in order to find these things. So we're going to be assuming that our forces are perpendicular, that at right angles to the area we're trying to find. So, to give you an example, if someone said that this particular box, let's imagine that this box had a weight, and this weight was, let's say, 100 newtons. So what we would have is, that would have been our force, so it would have been spread over. And if someone said that, well, maybe this particular box, okay, is half a meter right here by maybe, let's say this is 0.4 meters. So we can find out what the actual area is by multiplying length times width. And then we can find out what the actual force would be there. So here, in terms of pressure, what we would have is you would have to find the entire force, the magnitude of it. So in this case, this would have been 100 newtons. And then you would have had to find out what the area is. So that area for us, in this case, okay, is nothing else but simply the actual 0.5, so length times the width, like so. And we would have been able to find out what the actual pressure is. And notice what you will get is the units. So in here, I used SI units. So force, SI unit is newtons. Area, it is meters squared. So notice meter times meter is going to give you meters squared. And that brings us to the actual unit of pressure. And that's how you're going to be calculating these particular pressures. So you're going to need whatever the force is, the perpendicular force, which is spread over a particular surface area. And now the smaller the area, so as if we had this box and it just kind of was much more vertical in a sense, and you would start to concentrate the actual force in a smaller and smaller area, notice here that because area is dividing, then if this gets smaller and smaller, then it is actually inversely proportional, which means that this is going to get bigger and bigger and bigger. So the pressure just keeps increasing when the area keeps decreasing. One of the nice applications, for example, is, if you want to poke through a needle and take someone's blood or something like that, or maybe, give some kind of an injection, you notice that the needles, okay, are extremely tiny because you don't need a huge amounts of force to puncture the skin itself, because you're doing is little force, but very, very tiny surface area can puncture, okay, the actual skin itself, and therefore, okay, the pressure would have been very high because of that area being tiny. So within here, so if I kind of go back in here, it brings us to this concept of the units. So notice, in SI, the force is always kind of in newtons. Okay, the area is in meters squared. Now, meters squared is actually kind of large, but this SI unit is referred to as Pascal. So here, okay, I kind of spell it out here for you. It's named after a scientist, and Pascal, and these double dots and equal just means is defined as Newton over meter squared. So these two things mean the same. So Newton over meter squared is just pascals, and it's the standard. But you're going to see many different units for pressure if you're going to be continuing on. So for example, you might see units like this, which just means pounds per square inch. So instead of using newtons, they might use pounds, and instead of meters, they might use inches. And if you square the inches, you get inches squared. So you get pounds per square inch. So that's common. Sometimes you see it in tire pressures, and you actually do see it in others, kind of in engineering applications for various things, okay, that you may have. Now, there's another unit. So for those who maybe are in healthcare, or if you're interested in health in general, you might run into millimeters of mercury, and that's another unit. It's kind of used for historical reasons that you have, and millimeters of mercury is used very typically for blood pressure even to this day. So, you know, a reading of, let's say, 115 over 80, those numbers are in units of millimeters of mercury. So you're going to run into this unit as well. You might run into ATM, which just means atmospheric pressure, and there are actually a few others as well, right? So that's what you will have. And like any unit, as you go back and forth, you can convert between them. And, you know, your teachers, or you might actually see what the conversion ratios are between the different units. Okay, so for here and in this video, I would want you to kind of concentrate on the fact of knowing that there are obviously many units for pressure, but the standard one is Pascal, which is just Newton per meter squared. Now, these pressures, right, as you look at the formula, not very complicated. But where they do come into play quite a bit, and something that you may study, is pressures related back to the actual fluids. So very often, okay, in fluids, because we do have quite a bit, okay, and we have to understand how pressures work in fluids. Now, fluids, if you kind of have forgotten, so fluid is possibly a liquid, a gas, or a plasma. I'm going to put up a link up above there if you want to just kind of review back between the different states and then what defines a fluid. Well, in fluids, it's interesting because forces are always present perpendicular to the surface of contact. So that is very interesting. And the reason for that is because there's really no shear forces within fluids. That's one of the reasons why they are a fluid. Right? So they just kind of roll over each other. They're not like solids where you can kind of take a solid, right, and then push on one end and then push on the other end, and then you're creating shear forces, right, which are in opposite directions, so you can start to bend this. You can't really bend the fluids itself because they just roll over each other and they'll fill whatever container, okay, that they're going to be trying to be placed into. So in any case, so I just wanted to point that out because it makes your life a little bit easier. Knowing that for fluids, you can always think that whatever contact they are in, the surface, the force itself is going to be acting perpendicular to that. So for instance, you know, you're going to be learning something like this where you might have, let's say, a glass, right? So if you have a glass which is sitting down and you fill it up, let's say, with water, it's of no particular kind of item of thinking like, well, you know, if you're thinking down, so the contact point, okay, that you have in here, so this contact point at the bottom, you know, you have all of this liquid which is sitting up above it, which obviously has a weight, so it's going to exert a force, okay, which is going to be perpendicular down on the bottom of this glass, and because that glass has a surface area, you can find out what the pressure is. But, Okay, the other concept is, which is a little bit trickier to understand, and you'll get there, but this fluid at any point, okay, is actually pushing on this glass right there, okay, as you have, and that's something that you will know. And what I want you to know, at least from this video, is that those forces that are pushing up against the glass, obviously they don't want to break the glass, okay, are always going to be perpendicular, okay, that you have in there. So in order to illustrate this even a little bit further, if you do take, you know, a glass, water, and any liquid inside, even if it's a gas, and let's imagine that we would put a ball in here. So if this ball is kind of placed in here and maybe held down, you know, maybe you're pushing it down just a little bit just so that it kind of stays in one spot. Well, what you're going to find is that these particular, so this liquid inside is going to create forces that are perpendicular, okay, to this ball. So they're kind of pushing on it all the way around. And you might say, how does that happen? Well, because keep in mind that that liquid wants to fill in the gap. You have taken up space there for that liquid, and it wants to go inside to try to fill it. But because this ball possibly is some kind of a solid, it's strong enough to withhold the pressure. But if the pressure is strong enough, it might just collapse it in because of the fact that the fluid is pushing all around. And of course, the ball has a surface all the way, so you can find out at any point what those particular pressure points are. All right, so this is kind of an introductory video, and what I want you to take out of this video is what the definition of pressure is, which becomes the force divided by the area. The force that we take is always the perpendicular force to the surface area that we have. The unit itself that we're carrying through, the forces are in newtons, the area is in meters squared if it is for SI units, but you can use any unit for force and any unit for area. You just might come up with a different unit overall. All right. Okay, so that is it for this introductory video with regards to pressures, okay, and its definition. Okay, looking forward to seeing you in other pressure videos as well. Bye, everybody.